So let me go back a little bit to the high resolution aspects. So what we've done, this work I've done in collaboration with Xiaobao Xu at Florida State. So it's a North Atlantic domain from minus 28 south to 80 north. And we increased the resolution from 1/12 to 1/25. For information, the viscosity was decreased as we went from 1/12 to 1/25 and kept it reasonably constant at 150. So this is part of a handful of model configuration at the resolution. Julien mentioned one at 1/60 degree that took place at Grenoble. And there's another one that NASA JPL also has run. So there are about 3 at that resolution worldwide. Okay, they're expensive, 500,000 CPU hours for 1 year. Okay. So here is the average mean kinetic energy over the domain. It's, as you see, as you decrease viscosity, as you go from 1/12 to 1/25, you double the amount of mean kinetic energy within the system. Since we roughly kept the same viscosity in the 1/50th degree, they're about the same level. The increase is associated with the more sub-mesoscale activity. So systematic bias. So first, we're going to focus on the Gulf Stream separation and penetration. On the left is the mean sea surface height, the best estimate that Aviso, the CLS is putting forward. That's the latest, the 2013 version, where you see separation and air recirculation takes place. Currently, this is 1/12 degree. This is for HICOM, but I think Yann can confirm that all the other models have similar representation of separation and penetration. The recirculation is confined west of the New England seamount. As we increase resolution to 1/25, you actually get an increase in the recirculation south of the Gulf Stream here, but not really better penetration. It's only at 1/50th degree that you start to have a representation of the Gulf Stream and penetration that resembles more closely the observations. And one way to look at it is that you can look at the slope that you can derive from XBTs, or measurements of temperature that were taking place underneath a satellite track. And that's what we call in situ, which is a black version here. And then if you look at the latest Aviso, which is the dashed line, you see it falls pretty much on the top of this in situ measurements. Actually, as a note, if you look at the one that had a few years back, it was quite different. And the main reason is that it was taking into account floats that lost their drogue. Therefore, they were overestimating the strength of the circulation. So here, as you go from 1/12 to 1/50th, you see that the slope is increasing, and you're getting closer to the observation as you increase the resolution. You can also compare to cross-section velocities done by the Oleander between Bermuda and the United States. Here is the observations, and you can see that the mean position moves a little bit further north and becomes a little bit in closer agreement, but still the spread is still a little bit wider in the 1/50th than it is in the observations here. You can also do some broad measurements. Look at the Florida current in the Florida Straits, observes about 32. What I forgot to mention is that this simulation is using the same wind forcing year after year. There is no interannual variability. So, but it's a bit higher in the 1/25th and 1/50th, and a little bit lower in the 1/12 at brackets. The overturning circulation is pretty stable, which is not surprising given the fact that we're providing relaxation to climatology of the north and south. So here it's just a couple of movies. At the bottom is a 1/12th degree, that's the sea surface temperature, and at the top the 1/50th degree. So if you look at this, at first glance, they're not that different. Except that if you pay attention to the penetration, you'll see that the jet is usually, especially now, is much more coherent all the way to the interior, and it stops very closely here. Where you really start to see the biggest difference is when you start to look at the vorticity. It's a little bit washed out, but you see that you have a lot of small-scale structures compared to the 112. This is, so if, so now we're in the summer, so we see exactly the same thing that Julien showed before, where you have the sub-mesoscale activity in both, is much less reduced in the summer, and as we start to become more in the winter, you start to see in March, you will see an explosion of sub-mesoscale activity here, okay, right now, but much less, of course, in the 112. So here's the same type of plot that Julien just showed. So that's in the summer. You see at the 150th degree, you don't have a lot of sub-mesoscale activity. The saturation in the blue and the red is a bit different from Julien's. But here you see, the explosion, same thing that you see in the. So what I'd like to now talk a little bit more is about the sea surface height, or the variability at the surface that is induced by that resolution. So this is based on altimetry. This is the Aviso product, 112, 125th, 150th. So what you see here is that the eddy kinetic energy, or the variability, is confined west of the New England seamount in the 112th degree. 125th degree, it still does not really go further east than the New England seamount, but a lot of eddy kinetic energy that is concentrated south of it. When you go to the 150th, suddenly there is a regime shift. The inertial recirculation takes place, and you start to have a better agreement between the two. So more energetic in the 150th, and that's what I'm going to get back to in a moment. So this result was actually put together quite a few years back. They're used by the Harley Herbert and Pat Hogan, who used the simple 6-layer hydrodynamic models going all the way to 164th degree. And they found a little bit the same thing. 116, 112, that the penetration was bigger, also EKE, but not a penetration. It's only when they went to 164th they started to have a better representation. So it seems like this result that we find again with HICOM 15 years later is robust. So now let's look at a section at 55 West where we can compare two observations. This is a mean zonal velocity. This is moorings that were done in the 80s by Phil Richardson. And you see how the penetration of the velocities go all the way to the bottom. If you look at the 112th degree, it's pretty much, you have two columns dissociated here. There's no penetration to the interior. It's been shown by also a paper by Rob Scott et al. 125th, you start to see a better penetration, and on 150th, you see the coherence and the bottom intensified flow here. This is actually better seen by looking at the eddy kinetic energy at that section. So at the top, the 150th, and here the 125th, and so the better agreement is again with the 150th here. So one of the questions that we ask ourselves is, why is the eddy kinetic energy in the model higher than the Aviso? Well, Aviso is based on satellite measurements. There are every 10 days, there's this grid spacing between. There's some averaging that is being done. It's presented on a 1/8 of a degree, 1/4 of a degree grid. So, and also so two things. First one is just if you look at the EKE, so that's one aspect that is often done when you compute the EKE from altimetry is looking at the geostrophic velocity and not the full velocity. So here is a comparison in the 150th degree HICOM with and without geostrophy. So this quantifies the geostrophic contribution to the system. So it does exist, and the main reason is because you have a lot of eddies that are in gradient wind balance instead of basic geostrophy, and that's the reason why you see most of the difference north and south of the Gulf Stream. The Ekman contribution is actually pretty small throughout this thing. So the other thing that we look, Julien talked about power spectra. He talked about kinetic energy. You can do the same in sea surface height. It gives an idea or representation of the turbulence at the various scales. So this is a 112, 125th, and 150th. And as you increase the resolution, you see that the spectra extend further before dropping down. The slope is about k minus 5, which is, for this is done over that domain, which is a representation of what we call usually QG turbulence. Okay. And if you do it elsewhere in the domain, you start to move away a little bit from that balance. So now, how do we evaluate the impact of the altimetric sampling and the time average? So what we did is we subsampled. So in black is the power spectra of the Aviso product, okay? And in red is a 1/50th degree. So if we simply just project on the grid, on the 1/4 degree grid of the Aviso product, this is in green. So you see the cutoff, instead of being much smaller in the 1/50th, becomes to be here at the 1/4 degree grid. Now, if you add 10-day average, you see that you start to have a slightly different. You lose some of the energy in that scale here. And now if you do also 150 kilometer bandpass, which is what the optimal interpolation does when computing the Aviso product, it's also in the dark blue. So once you combine the two together, which is in purple, you see that it starts to fall back pretty much right on top of the... So the main conclusion from this is that the difference between the EKE that we find in the 1/50th and in the Aviso product is due to the way the sampling is done. So what you can look at is so that's the EKE based on geostrophic velocity on Aviso. This is a 1/50th degree with everything. Once you do the 150 kilometer bandpass, you see you start to have a reduction. And then when you do the two together, you start to have a field that is much closer to Aviso. You still have a little bit of a extra EKE, a little bit south of the New England seamount. And that's something that the model, that we need to find out exactly a bit why the model, maybe the way the barotropic, baroclinic, and the interaction with topography, bottom drag is taking place. So in summary, I would say that there is a significant improvement in the Gulf Stream representation at 1/50th degree. There's a bit of a regime shift that is taking place. And my hand-waving argument is that the increase in eddy activity, or especially sub-mesoscale eddy activity, allows the inertial gyres to actually establish themselves north and south of the Gulf Stream, which they do not take place in the other ones. And that time and spatial averaging is one of the main reasons between the observed difference between the altimetry and the model EKE, at least in this simulation. Side effect is that side comment is that the geostrophic component always cyclonic, therefore you have a difference north and south of the Gulf Stream, which is important if you just use the Aviso product and derive only the geostrophic velocity. Do not forget that there's an geostrophic component that's often present. And that the power spectra, you can learn a lot from the distribution within the domain. So, thank you.